Welcome to Lesson 3 of Rhetorical Data Visualization. In this lesson, we focus on data transformation, which I like to describe as the step in the process where we decide what to visualize as opposed to how to visualize it. Let's take a little step back and try to reason about what is data visualization. Well, data visualization is often described as the process of going from data to a visual representation of the data through a step that we can call visual mapping that maps data properties to visual properties. However, what this simple model misses is something that is really important, which is the data transformation steps that often happen in between these two stages. So a more accurate representation of what normally happens when we create data visualizations is that we start from raw data, which is typically collected by somebody else, or sometimes we collect the data. We have a data collection process. And then we have a data transformation step to produce the information that we want to communicate through visual mapping by creating a visual representation. So this intermediary step is part of the design process and is the step that allows us to decide what is the shape of the information that we want to extract from the raw data before it's visualized. So an example can give you a better sense of what I'm trying to communicate here. This table on the left represents vehicle collisions in New York City. So what you see here, every row represents one collision and every column represents one property of these collisions. For instance, we have the crash date, the time, the borough where this collision happened, the zip code, the latitude and longitude, and so on. Now, imagine that we want to answer the question, how many collisions take place in each borough? And how do the boroughs compare in terms of collisions? Well, we can come up with a bar chart like this one, where every single bar represents one borough. And the height of the bar, the length of the bar, represents the number of collisions. Now, try to think for a moment, try to compare the information that we have on the right and the information that we have on the left. I think if you think about it for a moment, you quickly recognize and realize that there's something missing in between. There's some steps that are necessary in order to produce the information that is depicted on the right. Well, here what we need in between is what is called a selection and aggregation step. The selection means selecting one of the columns, in this case the borough, and then calculating, aggregating across all these rows, selecting the boroughs, and counting for each borough how many collisions are there, which in this case is represented by the number of rows that have a given borough. Okay? So what the data table that you see in the middle here represents the actual information that is represented in the bar chart on the right. So once again, before we are able to represent the information that we want to communicate, we need an intermediary step where the raw data is aggregated and some counting procedure is performed. So one way I like to think about this is that in the data transformation process, we basically select what are the objects that we're going to represent and what are the attributes of each of these objects that we're going to represent. So we have which objects will be depicted, and since they are depicted, we will also make comparisons between them. And then what are the attributes or properties that will be depicted for each of these objects. So in turn, what happens is that we have different possible transformations starting from the raw data, and different transformations lead to different collections of attributes and objects. But different collections of objects and attributes lead to different visualizations. And different visualizations lead to different messages and interpretations. So there's a long chain here. And what I really want to communicate here is that data transformation is a key step and has a really, really relevant impact on what kind of messages you will be able to send with a visual representation and what will be the interpretation from the side of the readers. So let's take a look once again at the same data table, and I want to give you a couple of examples that exemplify what I just said. This is exactly the same table. So if we select the borrow and count the number of collisions, we have the bar chart that I've just shown in the previous slides. So now let's say that we look at the crash date and we count the number of collisions for each month, okay? Well, now we have a different visual representation that is more appropriate. We have a line chart that shows how the number of collisions across the whole set of borrows evolves over time. But if we select latitude and longitude, now with this information, we can look at where the collision happened on a map, for instance. So as you can see, just by selecting different attributes or different columns from this data table, we generate different objects of interest, right? And because we have different objects of interest and different data types, we also tend to have different types of visual representations. Not only that, when we decide what objects to represent, we can also decide to include or remove certain sets of objects. So in this case, for instance, I have once again the same data set where we are looking at different, again, the temporal evolution of number of collisions, and I believe this is by zip code. There are many zip codes, and the chart that you see on the left has all possible zip codes, and the chart that you have on the right are selected zip codes of interest, right? As you can see, the decisions of which element to include has a big impact on what is visible and what trends will be, the readers will be able to observe, and also what objects will be compared. Another example here, I can choose different granularity. So I can choose to represent time at the level of years, at the level of months, at the level of individual days. And as you can see, the kind of patterns that we can observe is very different. We call these different levels of granularity, and we're going to cover it in much more detail later on. So this is just to give you an example of the fact that there are many possible transformations, and these transformations have a big influence on what is visualized and what kind of information can be extracted from the visualizations that we build through these data transformations. So all these changes derive from data transformations. So now, after seeing that data transformation is such a relevant step, the next question is what kind of transformations exist and what is their effect on framing and interpretation. Effectively, at the end of the day, what we're interested in is to understand how these steps have an effect on interpretation. Well, why do we care about that? I would say there are two main reasons why we care about that. The first one is because if we are designers of data visualizations, we want to be able to predict what information readers will be able to extract or will be induced to extract. And if we are readers, we want to be able to assess the meaning and the truthfulness of these visualizations. And as we will see later on, there are many situations where the specific choice that one makes in terms of data transformation can make certain data visualizations more or less truthful, or sometimes even misleading. So what are the transformations that we include here? Of course, this is not a complete list. There are many possible transformations, but here I'm focusing on those that are more common and more impactful. So the first one is variable selection and grouping, which is very similar to the example that I've shown at the beginning. The second one is aggregate statistics and derive data. The third one is filtering and range effects. And the fourth one is granularity. So, as I said, more transformations exist, but we will focus exclusively on this specific one because they tend to be the most common and the most impactful. The first type of transformation that we consider is variable selection and grouping. This is exactly the same as the one that I just mentioned in the previous example. So let's dive a little deeper into what selection and aggregation mean. First, it means that we will have to select which columns from the table we will use to extract the information that we need. The second is how the values extracted from these columns will be aggregated. So this is exactly the same example that I've shown before. So selection is which column or columns I select, and aggregation is the strategy that I use to aggregate according to the elements that are in this column. In this case, all the rows that have the same borrow are aggregated to be part of the same group. And then a summary statistic function is calculated on top of each group to count the number of elements that are within the group to generate the table that you see in the middle. So what are the relevant factors in selection and aggregation? First, the selection of a variable or column to decide how to create the groups. So if I select borrow, the groups will be based on the borrows that are within this column. The second one is a column, variable or column, to calculate the quantity. So in the previous example, the quantity is calculated just by counting, so it doesn't require an additional column. But let's say that we use another column that, as we will see in a moment, contains information about how many people have been injured within a collision. Well, now I have the column selected to generate the groups and another column selected to generate the quantities. And the third element that I need is a method to decide how to calculate a summary statistic, an aggregation on the quantities of the elements that are within each group. So here, for example, we start from the same data set, but we choose two separate different columns to create the groups. The one on the left is the familiar set of borrows we have just observed. The one on the right is the contributing factor of the collision, which means what contributed to the collision. As you can see, we have the same type of graph, but different objects. The second element is which column is used to calculate the quantities. In the previous example, is just count, so there's no variable or column selected to calculate the quantities. But the one on the right, we selected the number of persons injured and used as an aggregation function the sum. So all the elements that are within the group, for the column that represents the number of persons injured, all the values that are within the group are summed up. And as I said, we can use different type of aggregate statistics. So if we focus on number of persons injured, we could sum the number of persons injured within each group. Or, for example, as we show in the graph on the right, calculate the average number of persons injured per collision. And as you can see, we have different trends. So what I want you to notice is that we started from exactly the same data set, the vehicle collision data set. We used exactly the same type of chart, but we represent completely different information and completely different trends according to what variables are selected for aggregation and what is selected as a quantity and what is selected as a function to generate aggregate statistics out of these quantities. So I want to highlight the idea that this step is really, really important. Even keeping constant the data set, the initial data set, the raw data, and the type of graph, we can generate many different charts and communicate very different information. So here is just another example to give you another example of the same idea. Here I again aggregated the data by borrow or by contributing factor, but also by the date of the collision. And the consequence is that I have two line charts. So again, same original data, same type of chart, but completely different comparisons and completely different trends. In the chart on the left, I compare trends over time by borrow. The chart on the right, I compare trends over time by contributing factors. So I want to conclude this part by mentioning what is the effect on interpretation. There are two main effects. The first one is about which objects are depicted and compared. I want to stress this idea that selecting what objects are in the visualization has an impact on which objects will be compared. And comparison in visualization is one of the fundamental tasks. If you think about it, we're always comparing objects according to their properties. So the second step is what properties are used for comparing the objects. You can think of properties in terms of, for instance, the quantities that we have just observed in these charts. So what objects are depicted, which also means compared, and according to what properties. So for instance, what numbers are calculated from these objects. The second type of transformation we consider is aggregate statistics. We have already seen some of these types informally when we looked at counting the number of collisions or summing up the number of injuries, creating averages, and now we dive deeper into what kind of statistics, what kind of aggregate statistics exist, and what are the implications of using these statistics, and also what are some major potential pitfalls. So we're going to cover a small set of aggregate statistics. These are by far the most common, but also the ones that can create quite a lot of problems. So what is an aggregate statistic? In general, the idea is that it's a number that is generated using several numbers that are aggregated into one that represents a property of a group. So what are the pros and cons of using aggregate statistics? Well, the pro is that they're absolutely necessary to summarize information and eliminate noise. So if you think about the previous examples that I gave, if I want to perform an analysis at the level of certain groups, like we looked at the borrows, we looked at the contributing factors of collisions. If I want to be able to attach descriptive values to these groups, I have to have a way to summarize quantities that exist at the level of the individual elements that are within this group and attach a number to the group rather than the individual element. So in our case, in the previous example, we had individual collisions, but I aggregate collisions to say something about the borrows. So I need a way to aggregate these values at the level of borrows. So absolutely necessary, and also necessary to eliminate noise, because the individual elements may have a lot of variation, but what we want to see often is the trend that shows up in specific groups or, for instance, over time. What is the downside of that? Well, the downside is that, of course, the aggregate statistics hide information. Instead of having all the individual values, we have an aggregate value, and necessarily as soon as we aggregate, we hide some information. So in general, there is always a trade-off between these two elements, the aggregation element and the summarization element, to eliminate noise and let a signal come to surface, and on the other hand, hiding information. So in general, when there are too many details, a visualization can quickly become confusing because there are too many elements. But if we have too few details, it may very well become misleading, as I'm going to show in a moment. So what aggregate statistics will we cover? We cover counts and sums, averages, and percentages and rates. So let's start with counts and sums. So going back to our running example, if I have a question like this one, what are the most dangerous boroughs? Well, think for a moment how you would answer that question given the data that we have. What are the most dangerous boroughs? Well, one way to do that is to reuse the same graph that we had before. So for every single borough, we count the number of collisions. So now the question I pose to you is, what can you conclude from this chart regarding the danger of driving in New York City? So I guess that your answer would be something like, well, Brooklyn seems to be the most dangerous spot, followed by Queens, and maybe then Manhattan and the other boroughs. Okay? Well, let's look at another plot, this time calculating the sum of people injured by borough. We saw this chart before as well. So what can we conclude from this chart regarding the danger of driving in New York City? Well, same thing, right? So there are lots of people injured in Brooklyn and Queens. Okay. However, the problem here is that if you think about it for a moment, the more cars there are in a region, the more collisions there will be. And we do not really know how many cars there are in each borough at any given time. So in other words, when we look at these two charts, the numbers that we are visualizing here are heavily influenced by how many cars are in that region at any given time. So in general, if there are way more cars going on in Brooklyn, right, and more people in general driving in Brooklyn, well, it's normal that there will be more collisions, but this doesn't necessarily mean that that area is more dangerous. It only means that since there are way more cars, there are way more opportunities for cars to generate collisions. Okay, so another way to look at this question is to calculate, instead of the number of collisions by borough, we can calculate the average number of people injured in a collision. Remember that in every collision, we have the information about how many people have been injured. So now we can take the average number of people injured in a collision. And as you can see, we obtain a dramatically different trend, right? So now it looks like that the average number of people injured in a collision tends to be pretty high in Brooklyn and the Bronx, but lower, but not dramatically lower in Queens and Staten Island, and much lower in Manhattan. So if you compare the chart on the left and the chart on the right, they tell a completely different story, even if in principle they both could answer the question which borough is more dangerous. So I think that's a really interesting point. So in general, one problem that we are facing here is something that is called the base rate bias. The base rate bias comes up every time the numbers that are shown are influenced by the number of elements that exist behind each group. If the number is influenced by how many people there are in the groups. So here is a different way of visualizing exactly the same data. In the map on the left, we have data calculated at the level of zip code this time and shown through a map. And we have the number of collisions on the left and the average number of people injured in a collision on the right. As you can see, the patterns, the geographical patterns that exist in these two maps is completely different, and you can conclude different, you can come up with different conclusions, right? But in a way, the one on the right is a better answer to the question which area is more dangerous, because the one on the left is highly influenced by the number of cars or people that live or pass by a given region. Okay, so this is a very general problem, and it's very common in maps. So when there are values that are represented on a map, it's always important to imagine or to ask yourself, is this value potentially influenced by how many data points are behind this group? A technical term that is often used is the sample size. Is the sample size non-uniform, and are the values influenced by that? In general, every time that we use count or sum, since they depend heavily on how many objects are within each group, counting the objects or summing up the values of the objects that are within each region is heavily influenced by how many elements are within each group. So now we look at averages. In general, there are, with the term average, we can mean a different type of metrics or aggregate statistics. Here we look at the two main ones, which are the mean and the median. And I want to highlight what is the main difference between these two. So imagine that we have this very, very simple data set that it's a collection of measures, right? And the mean is just the sum of these values over the number of values that are in this data set. Very, very simple. So that's the calculation, and outcome is 2.2, okay? But the median is calculated differently. You take the list of values that we have here and you sort them according to their value, and then you take the value that is halfway. Okay, so what is the main difference between these two? Well, the main difference is that the mean is heavily influenced by potential, what is called outliers. So if there is even one element that is a very, very high value compared to the rest, or a very, very small value compared to the rest, the mean will be influenced by that, as we will see in a moment in another example, right? But the median is not as influenced by these extreme values. So in general, the median is way less sensitive to extreme values, whereas the mean is very sensitive to extreme values. In general, another element that influences the mean is how many values are in the data set. So the influence to the extreme values also depends on how many numbers, how many elements there are. The more elements, the more values there are, the less impactful the effect of extreme values is. But if we have only a few elements, only one extreme value can heavily skew the mean in one direction. So one common problem that we have with these average statistics is hidden variability. So every time we visualize, for instance, like here with a bar, but we could use a different visual representation, the average statistic, what we are doing is we are hiding the variability that exists at a more granular level. So here is a great example taken from a paper called Beyond Bar and Line Graphs, Time for a New Data Presentation Paradigm, where they advocate for almost never using these aggregate statistics, but trying to use data visualizations that show the actual distribution of the individual elements. So what you see here is that you have many different potential data distributions, the one that you see in B, C, D, and E, leading to basically the same couple of bars, despite the fact when the median or the mean is calculated, despite the fact that the distributions are very, very different. So you can imagine that if we use only the bars to represent this information, we will lose a lot of information, very important information, about how these data set are distributed. A very relevant example of this problem is what is called the Anscombe's quartet. Anscombe is a statistician who invented this fictitious data set. So what is the Anscombe's quartet? Well, it's a collection of 4 separate synthetic data sets, the one that you see in these 4 quadrants. And the characteristic of these data sets is that they have exactly the same mean of X, exactly the same variance of X, exactly the same mean of Y, exactly the same variance of Y, exactly the same correlation, exactly the same linear regression, and exactly the same coefficient of determination. So if you're not familiar with all of these statistics, it's not really important. What is important here is that if we were to analyze these data sets exclusively through these summary statistics, we would completely lose the details that are so dramatically different in these 4 data sets. So it's incredible how when you visualize these data sets, you can quickly grasp that they are very, very different. They are very, very different trends. But if you were to use exclusively summary statistics to characterize them, you would completely lose this information. So this is always to keep in mind every time we use some summary statistics. So another element of the mean is what I was saying before. The idea is that the mean is highly sensitive to outliers. What is an outlier is one or very few extreme values. So take a look at these 2 pairs of bar charts. So there are 2 objects that are being compared according to a quantity, right? So in the bar chart on the left, A seems to have a higher aggregate mean quantity than B. And in the one on the right is the opposite. B has a higher mean than A. So if you were to try to imagine before I show you the details, what would be the distribution of these data points that you imagine are behind these 2 bar charts. For reference, let me go back quickly to this, right? Imagine what the distribution of these data points could be behind these 2 separate data sets, okay? Now, I created this example using the data set that I'm going to show you on the right. So look at this. The actual distribution of these 2 data sets look incredibly similar, very, very similar. The only difference between the two is the presence of one outlier in category A. So again, an outlier is one extreme example. So even one extreme example can skew the summary statistic, the mean in this case, in one direction and give a completely opposite result. Imagine if this is a result for some important scientific experiment, maybe, I don't know, in healthcare, right? So very, very, very important. The second aspect is the sensitivity to sample size, which again is something I mentioned when introducing the mean. What is a sensitivity to sample size? Well, to explain this idea, I'm using here another data set. This data set is always a New York City data set, but in this case it represents restaurant inspections in New York City. What is a restaurant inspection? Some officers are going to a restaurant and checking whether it complies with all the rules, typically regarding cleanliness, okay? And what I have here, so after each inspection, the inspector gives a score to the restaurant. And the score, so the higher the score, the worse the outcome of the inspection is, okay? And what I did here was to aggregate the scores by zip code, once again in New York City. And the color represents the mean or the average score of that region, of that specific zip code. So once again, a question for you. Try to think or look at this map and try to imagine for a moment what would be your conclusions regarding how the scores distribute in New York City, and also what are the regions that have particular trends, okay? So if you were to ask me and you show me this map, my first gut reaction, my first instinct is to say, oh, something is going on in this region here where the scores tend to be much lower than usual. There must be some really amazing restaurants here, super clean, right? And then I would say, oh, but there's a region here that tends to be quite bad. What is going on in these regions? It's, lots of problems in there. Okay. The reality is that these trends are not reliable at all. Why? Once again, we have to go back to the fact that the sample size, which means the number of individual elements that are within each group, can vary considerably between these regions. And if you think about it, if you think about what we have just said, regions that have a small number of elements, a small sample size, are way more dependent or way more sensitive to extreme values. Whereas regions that have a high number of elements are less sensitive to extreme values. In turn, this means that regions with fewer data points can very easily have extreme values because, let me say that again, very few extreme values lead to an extreme value at the aggregate level. So that's what, this is just a bigger representation of the same map, right? So some specific trends here, some extreme trends here. Okay, but if I now single out or isolate the regions according to the sample size, you will very quickly see what is happening here. So the one on the left are all regions with a very small sample size. And as you can see, they tend to be very extreme, both as high values and low values. Whereas the one on the right are the regions with a high sample size, large sample size, and they all tend to be in the middle. There's no extreme values, okay? They are much paler, okay? If you look at the color map here, pale colors represent elements that are way more in between, okay? So that's what is happening here. Another way to look at the same trend is through this scatter plot. What do we see in the scatter plot? Well, every single data point represents one zip code, and the data point is placed in this scatter plot according to the restaurant count and the mean score. The restaurant count is the sample size. So the more a point is towards the right, the more that region, that zip code, as the higher the number of restaurants that are within that zip code. And on the vertical axis, the higher the average, the mean within that zip code, the more towards the higher on the vertical axis is going to be, or lower on the vertical axis is going to be if the score is low. And what do you see here? Here you see the classic funnel shape, which means that as the restaurant count reduces to very few restaurants, very few numbers, a small sample size, the higher the variability of the mean score. Okay, there are more chances of having extreme values. So in turn, going back to the map, this means that when you see something like this, you can't directly conclude that there are specific meaningful trends in terms of high or low values, because the fact that there are high or low values depends exclusively, or almost exclusively, we don't know, to the sample size. So once again, another area where one can get fooled very, very easily. And now I want to conclude with the third class of aggregate statistics. Now we talk about percentages and rates. So the important thing about percentages that are, by the way, ubiquitous, it's very, very common to hear statistics that are based on percentages. One first thing to realize is that percentages are used to represent many different kind of entities or quantities. So they all look the same in terms of being a percentage of something, but in practice they are very different in terms of what they represent. So, for example, a percentage can be the part of a whole, right? There's a whole, and then there are segments of this whole, and these segments represent a percentage of the whole. So in order to talk about percentages, I'm going to use an example regarding a university that has different departments and statistics about students. So if I say 10% of our university students are in engineering, right? Now there are many different schools within the university. The whole set of school constitutes the entirety of the university, and there are parts, right? And the part represented by engineering is 10% of the total student population. Okay, but that's not the only way percentages are used. Percentages are also used to represent a change or a difference comparison. So typically between two or more time steps or two or more conditions. Very often in science, for instance, there's a comparison of different conditions. So if I say the number of students who graduated went up 10% compared to last year, now I'm talking about how the a rate here has changed from one year to another. So the percentage is more representing a rate of something rather than the part of a whole. And the last one is percentage as outcome, also what is called incidence. So if I say 2% of students drop out within the first 2 years, that's once again a rate. So it represents how many out of all the set of students drop out in the first 2 years. Okay, so these are 3 different interpretations of percentages. And percentages have a very peculiar way of misleading. They're it's really easy to get fooled by percentages. And here I'm going to list some of the most common ways in which percentages can be at least confusing, if not misleading, with the caveat that there are way more, okay? I think these are some of the most common. And we have the difference between percentage points versus percentage change, which I'm going to describe in a moment. Then we have percentage change over time or between conditions. And then we have percentage change of small values. So let me show you how these 3 types of percentages and comparisons can often mislead. So let's look at percentage points versus percentage change. Let's look at this statement. The number of engineering applicants increased by 5%. So I want to encourage you to think for a moment about what this 5% means. Let's imagine that is the increase between previous year and current year. Okay, it doesn't really matter. So what does it mean that it increased by 5%? How is that 5% calculated? Try to think about it for a moment. Well, the interesting thing is that there are at least 2 separate possible interpretations. The first interpretation is that the percentage went up from being 15% of the total applicants to 20%, right? So previous year, 15% of the whole applicants was 15. This year, the percentage of the total applicants is 20%. So it went up 5%. That's a legitimate interpretation. But it can also be that the number of applicants increased from 2040, just a number, to 2052, which represents a 5% increase. 252 is a 5% increase compared to 240. So as you can see, it's exactly the same sentence, but completely different interpretations. The second one is percentage change over time. This is very common to see how, often you have a line chart showing or a bar chart for every point in time, maybe different years or different months, how much something has changed. Okay. Again, here there are 2 possible options. One is the percentage change with respect to the previous value or the previous point in time. For example, in finance, if I'm looking at information about the stock market, it's very common to see something in relation to how much it has changed in percentage compared to the previous time. So if I have something like 5%, 5%, 5%, 5%, and so on, it means that something is continuously growing, even if that plot is going to show a somewhat flat trend, because that trend is in terms of percentage. Okay, but percentage over time can also be changed with respect to a reference value, to a constant reference value. For example, in climate change, it's common to look at percentage change with respect to the average across all the years considered. So that change is more like that year is that percentage above or below the reference value. So once again, it's very important to be mindful that when we look at percentages, they can have very different interpretations according to how they are calculated. And the last element that I want to highlight regarding percentages is the problem of percentage change when the number of values behind these percentages is very small. or the sample size is very small. So very similar problem to what we considered previously regarding the problem of sample size and the base rate bias. So if I say the number of students in my class increased by 50%. Now try to imagine if this 50% is a big change or not, right? If I tell you the number of students in my class increased by 50%, maybe again between previous year and current year. So it seems like a pretty sizable difference, right? 50% more students in class is pretty consistent, pretty big as a change. Okay, but I can have two cases here once again. So imagine two different situations. The first situation is a situation where the course increased the number of students from 2 to 3, whereas the other is a course that increased their number of students from 40 to 60. I think I don't have to convince you that these two cases are very different. So once again, there's an effect of sample size. If the number of elements behind percentage change is small, right, it tends to be way less relevant and reliable than when these percentages are calculated according to much larger sample sizes. So I want to conclude by once again mentioning what are the main effects on interpretation. So when we are showing visualizations to others, how is the interpretation of the information that is presented there influenced by the specific aggregate statistics that we decide to use? Well, first we saw that different statistics can and often lead to different interpretations. One example is the one where we aggregated data using the sum versus aggregating data using the average, right? These statistics can actually lead to different trends, and these trends can lead people to extract different information and interpretations from this data. And the second element is that some of these interpretations may actually be incorrect. So some statistics can very easily lead to misinterpretation. So one example that we saw is the problem of the sample size and the base rate bias. But we also saw that if we wanted to reason about how dangerous a given area is, if we look at the sum of collisions, is not as meaningful as the average number of people injured in that area. We also saw that when we look at percentages, the information can be easily misunderstood there because we don't know exactly how a percentage has been calculated and what it represents. We also saw, for instance, that if there are extreme outliers and we are using a mean value, we may get very different results, whether that single extreme data point is present or not. And in general, that is not a good idea to completely hide the distribution of a data set behind a mean. So in general, I would say the general message is we have to be really, really careful with aggregate statistics. As I said at the beginning, they're a powerful and useful tool because they reduce noise, reduce clutter, and let a specific signal stand out. But we also have to use them very carefully because they have a high potential to mislead people and potentially also to mislead yourself. The third type of transformation we consider is filtering and range effects. So what are filtering and range effects? Well, what often happens as part of the data transformation process and the design decisions one has to make is that we have to decide to represent a subset of the available objects, or a subset of the available values. Now, why is that needed sometime and useful? Well, first, to reduce complexity. There are many situations out there where if there are too many objects, it's very hard to visualize all of them. That's an example I gave at the very beginning. If there are too many lines in a line chart, all in a sudden you have a spaghetti plot and you won't be able to discern anything, for instance. But even in a bar chart, if you have too many bars, the bars end up being very small, so you can't really detect. You may actually miss relevant trends, right? And that's virtually true with every type of visualization. And the second is that sometimes we need to remove spurious information. We saw before outliers, and sometimes it's useful to remove an outlier, or there are many other elements that represent spurious information, and we might want to remove it. So for instance here, as I said, many lines, too much clutter, so reducing the number of lines can help. Or say here I have a bar chart where one of the bars represent all the null values in a data set, which means that a value is missing, has not been recorded, right? So do we want to have that bar there? Where it depends on the use case, but in general, there are many situations where we don't want to directly represent the missing values, even though, as a side note, missing values can create a lot of troubles. Okay. So this is, say, the positive aspect of removing information, or why removing information is often necessary and useful. So in general, I find it useful to think in terms of two types of filtering options, right? That are not mutually exclusive. They can happen at the same time. So filtering objects, which is the idea of reducing the set of items or objects, and the second one is filtering values, so restricting the range or extent of the values that are depicted. But this also comes with its own downsides, as often happens in visualization. So by omitting information, there's also a high risk of misleading, as usual, as we have seen for other choices that one can make in visualization. So the first type of problem is commonly known as cherry picking. There's a general term that represents the situation where a person picks only the data objects that are useful for comparing, for sending a different specific message, but it's only through the careful selection of those objects or those values that that message is true. And as soon as we zoom out or introduce other elements of comparison, the specific trend that was visualized is no longer that strong, or doesn't even hold at all. So here is a very simple example. We have UK national debt in percentage of GDP on the left hand side, and if we focus on this chart, one could send a message like, oh, the national debt is growing so fast and in a very dangerous way, right? But then if you zoom out and you look at the UK national debt over many more years, so a much wider time range, you will see that yes, that increase is definitely worrisome, but in the context of a much larger timeline, you see that it's not the worst increase ever. Okay, so this is a very common situation where the time range, if it's restricted, we can send a given message, but if it's widened, then completely different message comes out of it. Another example is cherry picking with objects. Here I created a fictional case where, say, there's a specific medical intervention, and we say that there's a public health agency, and let's say they want to show, or maybe a group of researchers, let's say a group of researchers that wants to show the effect of a specific medical intervention, and they start that intervention at a given time represented by this vertical axis, and they say, oh, look, the incidence of this problem is going down right after the intervention, right? But as soon as you introduce other interventions, that is not the only one that has been tested, well, those interventions don't show the same trend, right? So imagine how much stronger is the message when only one intervention, one element is selected, versus when the same intervention tried in other contexts shows these trends where only one goes down and the others keep being either flat or even increasing, right? Much less convincing, the one on the right. So by picking one single object, I can send a specific message, but as soon as I add more context, then that message doesn't hold anymore, or is not as strong as the other one is. Very, very common situation. So one way I like to think about this, almost like a way to counteract this problem, is to always ask yourself, compare to what, right? Compare to what is a really useful question to have ready, also sort of like as a neutralizing trick, right? So whenever you see something, whenever you see a visualization of any type, the question is, compare to what, right? So using the same examples, if I see this line chart here on the left, it's like, oh, the national debt is going up considerably, and then I ask, compare to what? Well, if we compare it to a much longer time extent, doesn't look as relevant anymore. And similarly, the medical intervention, compare to what? As soon as I put more objects to compare the medical intervention, we see that through the comparison, the message loses its strength. Okay. So general rule of thumb: always ask, compare to what. The last type of transformation we consider is granularity, or change in the granularity of the data. So the idea here is that very often in visualization, we can decide to change the level of granularity or resolution of the data that we have, so that we can make certain patterns more or less apparent, or focus on certain type of patterns. Here I have a few examples with different types of data. So for example, if we look at temporal data, we can aggregate quantities at the level of years, months, or weeks. And as you can see here, according to what level of granularity we decide to use, certain patterns are more or less apparent, right? So for instance, the timeline with the weeks granularity shows a lot of little details, right? But maybe at the expense of seeing the overall trend not as clearly as when we aggregate data at the level of years. On the other hand, when we aggregate at the level of years, we lose a lot of important details. So this is certainly not true only for temporal data. The same effect exists when we look at spatial data, and in particular geographical data. So in geographical data, it's not uncommon to have quantities at the level of macro areas, then areas within the areas, and different levels of granularity. So here is another example, exactly the same information, but presented at different levels of granularity. And as you can see, the trends that is possible to observe are very, very different. Same thing at the level of individual quantities. So here I have 3 histograms where the data, the quantity has been binned with different sizes of the bins. And as you can see, the one on the left produces a lot of little details. The one in the middle shows a very nice, very visible trend with not a lot of noise, whereas the one on the right completely hides the little hole there is in between the two main bumps. Okay, so this is just to give you a sense of the fact that granularity effect can be present in with many different data types and in many different type of visualizations. And also the second aspect is that as the granularity changes, as you decide to use different levels of granularity, there are certain patterns that become more or less apparent. So this is you can see this as another knob that you can twist, and it's part of the decisions that a designer has to make in order to figure out what is the best level of granularity to communicate certain types of information. So again, as in the other type of transformations, here there is always a trade-off, right? There are positive aspects of the change in granularity and negative aspects. And here I'm going to focus once again on potentially misleading aspects of aggregating or disaggregating data. The first one is called the ecological fallacy. So what is the ecological fallacy? The basic idea is that when we look at trends that are observed over aggregated data, it's common to make incorrect generalization. So in general, a trend that is observed at a certain level of aggregation doesn't necessarily extend when we disaggregate the data to the disaggregated data. So here I have a little mock-up on the right. So for instance, if I have a correlation that exists or is observed when the objects that we map in the visualization is at the level of countries, that same correlation may not hold when you look at the objects or the people or the events within each country. So it is possible that when you visualize some information at the level of countries, you see a strong correlation among in terms of country data, but that correlation doesn't exist or even reverses when you look at the same data within each country. A specific effect of reversing trend at different levels of aggregations is what is called the Simpson's paradox. So let me give you an example of how the Simpson's paradox can happen. I will use a fictional scenario, a fictional example. So let's say that we gather data about how many about students and how many hours they study for 2 different type of courses, an easy course and an hard course. And on the x-axis, we have the number of hours of study, and on the y-axis, we have the final grade. Well, for the easy course, what we see is positive correlation between the number of hours studied and the grade, as expected. For the hard course, we also see the same correlation. The more a person studies, the more typically they tend to get a higher grade. However, what happens is that for a hard course, on average, there are students spend more time studying, and they also tend to get overall a lower grade, right? Now, if we remove these 2 groups and group the data together through aggregation, what we get is an inverse trend, which is paradoxical. The larger, the bigger the number of hours, and the lower the grade, which is kind of counterintuitive. I'll show you a second example that looks a bit different, but it's still an example of paradox, Simpson's paradox. So let's say that we have the success rate of two hospitals. So we have the orange hospital and the blue hospital. And what you see here is every single dot is a procedure. And the color procedures are the ones that are successful, and the gray procedures are the ones that are unsuccessful. And when you look at these statistics, what you can very easily conclude is that the blue hospital is way worse than the orange hospital. But the situation is actually much more complicated than that. See what happens when I split this information into easy procedures and hard procedures. Well, the blue hospital, when we look at easy procedures and hard procedures, tend to have as expected, very high success rate for the easy procedures and way lower success rate for the hard procedures, as expected. But when we look at the orange hospital, not only we have the same trend, but we also see that when we do the comparison between orange and blue, orange always has a worse outcome than the blue hospital, both in the easy procedure group and in the hard procedures group. What happens, however, is that the orange hospital tends to have way more easy procedures, whereas the blue hospital tends to have way more hard procedures. So in turn, what happens here is that once we aggregate this data back into one group, since there are way more hard procedures in the blue hospital and the hard procedures have a much lower success rate overall, what happens is that the blue seems to have a much worse outcome compared to orange. But again, it's a sort of an illusion, because when this data is disaggregated, we see that the blue hospital is actually has a higher performance than the orange hospital. So this concludes the set of transformations that I wanted to discuss. As a recap, we looked at variable selection and grouping, aggregate statistics, filtering and range effects, and granularity. For each of these, I first explain what they are and how they work, and then I focus my attention on the many ways in which they can mislead if not used appropriately. So the main idea of this whole module is the following. So the data transformations imply what is visualized as opposed to how something is visualized. And then what is visualized implies what are the perceived messages. Because of that, deciding what to visualize is really important. And this means that you always have to think about how data transformations can impact the perceived messages, and also how they can potentially mislead. I want to conclude with a reflection on what are all these rhetorical choices that you can make. Ultimately, all of these choices in how you transform the data are rhetorical choices. And the first one is about which objects to display and compare in the first place, typically done by deciding what attribute or attributes to use to aggregate data. Second, what are the statistical aggregates that you decide to use? And we saw that according to which one you use, you can communicate very different messages sometimes. Filtering, which objects you decide to include or exclude. Ranges, and typically what are the values that you decide to include or exclude. Typical example that we discussed here is time range. If you focus your attention on a smaller time range, you can communicate a given message, and if you zoom out and see more of the time range, you can communicate a completely different message. And finally, what we just saw, the granularity level, and how using different levels of granularity makes certain patterns more or less apparent, or you can show completely different patterns. And the extreme case is the one that we just saw about the Simpsons paradox, where if you show data at a given level of granularity and you change the granularity, the patterns that can even completely reverse.